In this video, first I explain what is the functions of diffusers. Then after we derive steady flow energy equations for a diffusers by using these diagrams. So let's first we understand what is the functions of diffuser. It is a device that increase the pressure energy, means pressure is increased and pressure energy is increased of a fluid at the expense of its velocity drop. Velocity drop means kinetic energy is drop. Okay, so this diffuser is opposite to nozzles. Earlier we study about the nozzle. What is the functions of the nozzle? Function of the nozzle is increase the pressure energy by reducing its pressure energy. Okay, so opposite thing is done for the diffusers. The pressure energy is increased by reducing the velocity, means by reducing the kinetic energy. Okay, so in a nozzle kinetic energy is increased, in a diffuser the pressure energy is increased. Diffuser is a passage of varying cross section by means of which kinetic energy means velocity of the flowing fluid is converted into the pressure energy. Okay, means kinetic energy is converted into the pressure energy. So here you see that in a diffusers we supplied the kinetic energy, means fluid which have the higher velocity. Fluid means we supply suppose water, oil, anything to the diffusers which have the high kinetic energy. So at the outlet of the diffusers we achieve the high pressure energy, means at the inlet the pressure energy is lower and kinetic energy is higher. Okay, so at the outlet we achieve the high pressure energy and the low kinetic energy. So this is the main functions of the diffusers. The cross sectional area of diffuser increase in the flow direction for the subsonic flow as shown in the figure, and the increase for the supersonic flow. Means suppose that is a two type of the flow, subsonic and supersonic flow. In a subsonic flow the cross sectional area of the diffuser is increased, and at the inlet area is lower and at the outlet area is increased. And for a supersonic flow area is reducing, means at the inlet there is a high cross sectional area and at the outlet there is a lower cross sectional area. Okay, now we know that steady flow energy equations. Okay, first we understand this diagram. Here you see this is the diffusers. Okay, and diffuser is thermally insulated, means there is a no heat rejection, means we consider that the Q is equal to 0. Okay, but practically it is not necessary in all the diffusers the Q is equal to 0. Suppose we are not provide the insulation, then the Q have the some value. This is the inlet fluid in and this is the fluid out. So here you see there is the lower cross sectional at the inlet and the higher cross sectional area at the fluid outlet, means here diameter is lower, this diameter is higher, means diameter is higher and the area is higher. Diameter is lower means area is lower. Okay, means area is continuously increasing. So here you see in this deep point cross sectional area of the diffuser is increased in a flow direction of subsonic flow, means here we are considered the subsonic flow. Suppose we consider at the supersonic flow, then we need to draw the opposite diagrams. Okay, or we either need to change the fluid in and a fluid out at the alternates. Now this is the section section 1, that is a fluid inlet. This is the section 2, this is a fluid outlet. Here we consider one datum line. From the datum line we measure the height of the inlet and outlet, that is a Z1 and Z2. Now this is the basic steady flow energy equation, that is a M in bracket H1 plus C1 square by 2 plus Z1G bracket over plus Q equal to for the outlet. Okay, for the outlet here you see that is a two term is used. Then we mention everywhere two step. Okay, that is a M in bracket H2 plus C2 square by 2 plus Z2G plus W. Here we are not written M1 and M2 because what amount of the mass is entered they are same way exit. Okay, that's why we written only the M. For the diffusers no work input or output, so W is equal to 0. So in this diagram you see we are not supplying any work to the diffusers or diffuser not give any work. Okay, that means the W is equal to 0. No heat interactions between diffusers and the surrounding because it is a thermally insulated wall. That means Q is equal to 0. And the third is the Z1 and Z2 are equal, means Z1 minus Z2 is considered 0 because in change in potential energy is 0. Okay, so in every case it is not possible Z1 and Z2 are same. Suppose in some component or some system the diffusers are installed inclined, then the Z1 and Z2 value is different. Okay, so now we putting this value of the work done W, Q interactions and the Z1 is equal to Z2 in these equations. Okay, Then what equation we achieve? We achieve this equation, m in bracket h1 plus c1 square by 2. We consider z1 is equal to z2, so this term is equal to 0. q is also 0 due to these assumptions, okay, second assumptions, equal to m in bracket h2 plus c2 square plus z2g. So here we consider z1 is equal to z2, so it is 0, plus work done is also 0 according to first assumptions, okay. Now we further simplified these equations. Before moving ahead, I request to like the video and subscribe my channels for watching the more video related to the engineering thermodynamics and another subject of the mechanical engineering. For more video, link is provided in descriptions or a card, or you also visit the playlist. Now again we take the same example, same steps, because for our remember purpose, okay. Now we further simplify these equations. We cancel this m on a both side, okay. Then only remaining part on the left side is the h1 plus c1 square by 2 is equal to part remains on the right side, that is h2 plus c2 square by 2. Then we supply this h1 on a left side to the right side, okay, that means h2 minus h1. So here written h2 minus h1 on a left side, that is a c1 square by 2 is there, and we supplied this c2 square by 2 on a left side, then it is coming a minus, okay. So it is written c1 square minus c2 square by 2. Then we make the equation in the form of the c1, okay. During the studying the nozzles, we make the equation in a form of the c2. Why? Because in a nozzles at the outlet velocity is higher, means we make the equation in a form of c2. But in this case we make the equation in a form of the c1 because in the diffusers the inlet velocity is higher compared to the outlets, okay. So first we supply these 2 on the left side, so it is going to multiplication. So here 2 h2 minus h1. Then after minus c2 square is supplied on the left side, so it is converted in plus c2 square. Then we do the under root on the both side, then the c1 square is converted into the c1, and here we provide this under root. Now in case of the diffuser, c2 velocity of the outlet is very less than compared to the c1, so we consider the c2 is equal to 0, okay. So here c2 square value is putting 0, then we get this equation, c1 is equal to under root of 2h2 minus h1. Now if we consider that the working fluid is perfect gas, then instance of this h2 minus h1, we are able to return cp in bracket t2 minus t1s, okay. And for the perfect gas, another one law is that the t2 upon t1 is equal to p2 upon p1 raised to gamma minus 1 upon gamma. So here you see that this equation is replaced, means this h2 minus h1 is replaced by the cp t2 minus t1, okay. From this bracket of the t2 minus t1, we take the t1 common, okay. So here 2cp t1, so this t2 upon t1 because we take the t1 as the common, then minus 1. Then further we simplified, means we putting the value of t2 upon t1, okay. So this t2 upon t1 is replaced by p2 upon p1 raised to gamma minus 1 upon gamma. So here you see this equation, c1 is equal to under root of 2cp t1 in bracket p2 upon p1 raised to gamma minus 1 upon gamma minus 1. So this is the final equations for the diffusers. So thank you for watching this video. If you learned, then like the video, subscribe my channels for watching the more video, and don't forget to share with your friend.